Okay, good morning. There's one topic I want to do before, well, not topic. Actually, I want to show one slide and skip over the in-depth discussion of the topic, and that is Bode plots. And the reason is there is a question on the homework that's due tomorrow, and so I want to cover that slide so you'll be able to answer that question. It's a short answer question, and then we'll cover it in depth on Wednesday. Okay, so 03 and Bode plots. So H.W. Bode was an engineer working for Bell Labs in the late 1930s or mid 1930s, and he developed this graphical analysis technique where you could plot the frequency response of a system. Okay, and so it's widely used to plot the frequency response of filters and other time invariant systems in electrical engineering. What it does is it basically uses asymptotes to approximate the behavior of a filter circuit. Okay, so what we're doing is we are taking straight line approximations. Asymptotes, if you may or may not be familiar, but in geometry, asymptotes are straight line approximations to a curve that are tangential. And the approximation, basically, the distance between the approximation and the actual curve approaches zero as either one of the coordinates tends towards infinity. I simply like to state to students that it's basically a straight line approximation of different pieces of a curve. Okay, so if we take a low pass filter, for example, a low pass filter has a curve that looks like this, right? So I'm in the middle during the transition period, or the transition portion is the break frequency or the cutoff frequency FB. No matter what kind of filter it is, once you have a cutoff frequency, all the frequencies to the left are the low frequencies. All the frequencies to the right are high frequencies. Doesn't matter whether it's a low pass filter or high pass filter, right? Once you have a cutoff frequency, all the frequencies below that FB or cutoff frequency or break frequency are low. Everything that's higher is considered high. So a low pass filter has a curve that looks like this. This is the pass band. This is the block band. So if you had a Bode plot, you could approximate each portion, the low frequency and the high frequency portion, using straight lines, hence straight line approximations. Simply put, I could take a straight line and approximate the straight line like this. Okay. Then I could take another straight line and approximate the high frequency portion with a straight line that has a decreasing value, sorry, right? Decreasing value. Now, if you look at this diagram on the left, this is the low frequency asymptote, and this is the high frequency asymptote. So let me and technically the point where they meet is actually the break frequency. Okay, so what I have drawn on the right is not, that's just for explanation purposes. But in a Bode plot, technically, the point where the two asymptotes meet is at the break frequency. And that is more clearly illustrated in this graph right here. Okay, the meeting point is the cutoff frequency. Now, if you've noticed, the x-axis, usually we talk in terms of frequency. On here, it's multiples of frequency. And this is something that we'll talk in depth on Wednesday. So both of these scales, both of the axes, x and y, are compressed. Okay, so Bode plot is technically a plot of the transfer function in decibels as a function of frequency plotted on the log scale. Both the axes, the y-axis and the x-axis, are compressed. This allows us to plot a very wide range of data points on a small chart. Okay, so again, this is something we'll talk in detail, but I just wanted to give you this heads up so that you are able to answer the homework question. Okay. There is a slope of this line, so this is a decreasing slope. The slope of this line is always 20. It's 20 decibels per decade, 20 dB per decade. Okay, 20 dB per decade. For a first order system or a first order filter, it is always 20. For a second order filter, it is 40. Third order filter, it is 60, and so on and so forth. So the higher the order of the filter, the sharper or steeper the slope of that line. So let's say for a first order filter, it's 20 dB per decade. For a second order filter, it's 40 dB per decade. And so on and so forth. Obviously, there are trade-offs, right? And that goes into, filter design considerations. Remember, as I stated, filter design is a highly specialized topic in electrical engineering. There are engineers who pick this as their specialty, and they could spend their entire career in that field. Okay, so let's take a pause. Let me know if you have any questions. Any questions? So what would a Bode plot for a high pass filter look like? Let's say this is the break frequency, right? Break frequency. Frequencies on the left are low, frequencies on the right are high. A high pass filter would pass high frequencies. So the high frequency asymptote should be a flat line. Make sense? Right? High frequencies are passed. And then low frequencies are blocked. And so that would have a slope. And this time it's an increasing slope. So plus 20 dB per decade. Low pass filter, it's falling down. So it would be minus 20 dB per decade. Okay, low pass filter would be minus, high pass would be plus. Again, two lines, and you can approximate and display the frequency response of a high pass filter. Make sense? Okay. All right, then let's go into the example problem. Okay. So remember the example 1 from this chapter. We had a system whose transfer function was described to us graphically, right? We were given a input, V in of t was given, and we were asked to find V out of t, the output voltage. So it's a similar problem. The approach is similar, except that this time the transfer function is not given to us. Okay, the transfer function of the system is not given to us. We will determine which one to use. So here we have a filter circuit. And obviously from our discussions, we know what kind of circuit it is. But let's say you are given an unfamiliar circuit. You don't know what it does, right? You're given this circuit and you're asked to find the output if this was your input. Okay, V in of t is given to us, and we are asked to calculate V out of t. output voltage as a function of time. Okay, so V out of T is the deliverable. Values for the components are given, and V in is also given. Okay. First thing we do if it's an unfamiliar circuit is we perform the quick analysis using the frequency behavior of these components. So we would draw two diagrams for that circuit, one at F is equal to 0, second one, F is equal to infinity. And we model the component behavior at both those frequencies. Capacitors, open circuit, and short circuit for low and high frequencies. Right? So we have these two diagrams. Then we can see at high frequencies, capacitor behaves like a short circuit. Hence, V out goes to 0. V out goes to 0. Low frequencies, capacitor behaves like an open circuit. So whatever we give at the input, we obtain at the output. So low frequencies, we obtain output, yes. High frequencies, no output, 0. Hence, it is a low pass filter. And then we go to our tables and we choose the equation that corresponds to the low pass filter. For a low pass filter, transfer function is given by this expression. H of F is 1 over 1 plus JF over FP. Standard equation, whether it's RL or RC does not matter. If it is a low, if you determine it is a low pass filter, this is the expression you would use. If you determine it as a high pass filter, you have an additional term in the numerator, JF over FP. So again, you first determine what kind of filter it is, then choose the equation that you need to use. Once you have that, you calculate the break frequency FB. FB for a RC filter is 1 over 2 pi RC. Plug in the values for RC, calculate your break frequency. For this case, is 100 hertz. Okay, 100 hertz. Then we take a look at our input signal. Our input, similar to example 1 earlier in this chapter, is comprised of 3 components. We can break it down as V in 1, V in 2, V in 3. If we notice the magnitude, meaning the peak values and the phase angles for all 3 are the same. 5 with an angle of 0. So the phasors for all 3 components are exactly the same. 5 with an angle of 0. Okay. It doesn't make any difference. That's just, it's not even, I wouldn't even say that it makes it convenient or anything like that. Okay. It just is what it is. It doesn't really matter if it's phi angle 0 or 10 with an angle of minus 78. We simply still have to multiply and find our answers. Okay. So again, phasors for all 3 are the same, but the frequencies are different. And if the frequencies are different, we have to handle them separately. Okay, they are all independent frequencies, all independent signals. The 5 and angle 0 phasor doesn't mean much. We still have to handle them differently. So we have, first one has a frequency omega of 20 pi, second one is 200 pi, the third one is 2000 pi. We equate each one of these components to the standard expression and extract information about omega and then the frequency in hertz. The reason we want frequency in hertz is because all of our calculations, our transfer function equations, and FB are all in hertz, frequency F. If we choose omega, we can directly use the omega information. That is all. But again, our frequencies, our transfer function are given as a function of frequency, function of F. So we extract the function, extract the frequency information from the input signal, and we obtain F1 as 10 Hertz, F2 as 100, and F3 as 1000. Okay, 20 pi equal to 2 pi F. 200 pi equal to 2 pi F. 2000 pi equal to 2 pi F. We equate it with omega is equal to 2 pi F, and we obtain frequency information for all three components, F1, F2, and F3. Once you have that, you plug it into the equation for the transfer function, H of F. F over FB. F1 over FB gives you 10 over 100. F2 over FB gives you 100 over 100. And F3 over FB gives you 1000 over 100. You reduce those, you get an expression for H of 10, sorry, H of 100 and H of 1000. Okay. H of 10, H of 100, H of 1000. Program the equation into your calculators and you solve to obtain the transfer function in polar coordinates. If you perform this manually, this is how I would go. Let's say H of 10. H of 10, I need to perform a division, 1 over 1 plus j 0.1. So I would change that into polar coordinates. 1, of course, simply becomes magnitude 1 with an angle of 0. And here I would have magnitude and phase angle for the denominator. And then I would perform that division. Once I perform that, I obtain the answer as 0.9950 with a phase angle of minus 5.7. Let's take a pause. Think on that. Let me know if you have any questions. Yes. Just magnitude of, so this would be H of 10, 1 over 1 plus 0.1, j 0.1. And so it's the magnitude of 1 plus j 0.1. And then the phase angle of 1 plus j 0.1. Yeah. Again, this is only if you're doing it manually. If you have a programmable calculator, you can program that entire equation all at once, and it will give you the answer directly. And once you have, and the reason I've taken so many decimal places is to get a more accurate or precise value, just to show that there is a degradation of the signal. Even though we are in the low side, low frequency, meaning if you apply a 5-volt signal, we should obtain 100% of 5 volts at the output, right? But that's not the case. We only obtain 99.5% of the output. I mean, at the output. It's not 100%. So even at a low frequency of 10 Hertz, remember, transition between the pass and the block is 100 Hertz. My input is only 10. But even at 10 Hertz, there is a slight degradation of 0.5%. And then H of 100 is 0.707 with an angle of minus 45. This will always be the case when your input frequency is equal to your break frequency, because you would get FB over FP, which is 1. So you would always have 1 plus j in the denominator. So your magnitude at break frequency is always 70% of the input voltage. Doesn't matter what kind of filter it is, doesn't matter whether it's low pass, high pass, RC, RL, does not matter. It will always have a magnitude that is 70% of the input. And then H of 1000, of course, is very diminished, right? As it should be. It's a low pass filter, meaning higher frequencies, should be completely attenuated or diminished. Once you have h of f at each one of these frequencies, apply the standard equation. V out is h of f times V in, phasor form. You calculate all values and you obtain the magnitude and the transfer function. Sorry, magnitude and the phase at each one of these frequencies. Final answer is asked as V out of t. And so you perform an inverse phasor transform or a reverse phasor transform, and you write out the final answer. If I plot these 3 points, you can see this approximates a low pass filter. This is the pass band on the left, and this is the block on the right. The steps and the approach make sense. Okay. Note that in real life, we have these filters, right? We have to have a cutoff point. We can't wait for it to go to 0 because it goes to 0 very far into the future, right? So 3 frequencies, 10, 100, and 1000. If it was an ideal filter, we would say, okay, 100 hertz, after 100 hertz, output should go to 0, all the way to 0. But it's not 0. At 100 hertz, we still say if V in is 5 volts, the output at 100 hertz is still 70% of 5 volts, meaning you're still obtaining output. Even at the high end, 1000 hertz, you still obtain half a volt, 0.5 volts, or almost 0.5 volts. Your break frequency is 100, meaning anything beyond 100 should go all the way to 0. But even at 1000 hertz, we still obtain a half a volt. We consider that to be blocked. Okay. At 101 hertz, you would still obtain about 70%. We still consider it to be blocked. So real life, we do draw a line, and that line is the break frequency. And that is the point where the output voltage, so at FB, V out drops to 0.707 times your V in, but the power drops to half. Because power P is given by the equation V square over R. When you calculate that, V out, the voltage at the output drops to 70% of the input, but the power at the output drops to 50% of the input power. Hence, these are also known as the FB is also known as the half power frequency. Okay, FB is also known as the half power frequency. Okay, we'll end class here today. If you have any questions, I'd be happy to answer them. Otherwise, I'll see you all on Wednesday. Remember, homework is due tomorrow. If you have any questions, let me know. I won't be on campus tomorrow. I have a few appointments. So send me an email. I'll be happy to meet over Zoom.